Finally, we come to some other decompositions that are useful. It's helpful to be able to see some structure within a system. So the Schur decomposition uses a square matrix, and it basically says that every square matrix can be decomposed this way. AV is equal to V times, and instead of lambda, V times lambda, we have V times lambda plus n, where lambda is a diagonal matrix of eigenvalues, and n is an upper triangular nilpotent matrix. Okay, so nilpotent matrix again satisfies this relationship, and V is a unitary matrix. So one of the nice things about this is we can actually get the eigenvalues, and we get a unitary matrix that gives us those eigenvalues. Okay, so that's what we have. So U and T, so this is the MATLAB for that. So what is actually returned when you use this is not a diagonal matrix. This is actually the sum of these two, which is an upper triangular matrix. Similar to the eigenvalue decomposition, we have something called the spectral representation. And this is how that spectral representation is described. So it's kind of complicated, and we will explore more of this in detail. But let's just say that what this representation does is it breaks up our eigenspace according to projections. So for each eigenvalue, there is an eigenspace projection. And there is also an eigenspace nilpotent matrix in general. Okay? Those eigenspace projection matrices are not necessarily projectors. They're projections. That is, if I square it, I get the same thing back. This set of eigenspace projections they have certain relationships with each other. In particular, the sum of those projections adds up to the identity matrix. If I multiply two projection matrices together, I get, so delta ij means I get either 0 or 1. I get 1, this quantity is 1 if I equals j, it's 0 otherwise. So that is, what this is saying is, if I is not equal to j, I get 0. If I is equal to j, I basically have this same thing back. Okay, so that's what this equation is saying. And also each of the e's times a, it actually I can multiply. They commute with a. Each of the e's commutes with a. I can get them in different order. So notice that in general, matrices do not commute. So whenever you see matrices that commute, you know there's a special relationship between the two. And it turns out that A can be written in terms, or rather the E's can be written in terms of a polynomial in A. And so that's why they commute. The nilpotent matrices satisfy this relationship. They're all nilpotent. If I multiply the nilpotent matrix times a projection, I get either 0 or the nilpotent matrix back. If I multiply two nilpotent matrices by each other, I get 0 for any I not equal to j. And the nilpotent matrix itself can be written in terms of the projection matrix this way. So this is actually how we would compute the nilpotent matrix once we have the projection matrices. So this is pretty complicated, this spectral representation, but it's going to be helpful when we come to computing functions of a square matrix. So we'll definitely explore this more in detail. All right, we've already seen this kind of thing before. Any matrix, m by n matrix, can be factored into a product of two matrices, both of which are full rank matrices. So before we saw F and G is what we saw before. And in general, this is not unique. And so one way to do this, we've kind of seen this already, is we choose L by choosing the linearly independent columns of A, putting those into a matrix and calling that L, and then computing R from L pseudo-inverse times A. So we've kind of seen this guy already. That's the LR factorization, left-right. Then there's the LU factorization for a square matrix. LU is lower-upper, so this is a little different. Any square matrix can be factored into a lower and upper. L is a lower triangular matrix with unit diagonals, that is ones along the diagonal, and U is an upper triangular matrix. Okay, so this factorization is unique. Okay, so we have, that's a factorization, and there may be good reasons for factoring things so that I have two triangular matrices. The Q-R factorization, any matrix can be factored according to a Q-R factorization, where Q is an m by m real unitary matrix or orthogonal matrix. Okay, and where R is an upper triangular matrix. So the value of using this kind of factorization is because, especially when you have a large matrix A. If you have a large matrix A and you want to solve for, let's say, AX equals B, you want to solve for X. The Q-R factorization is helpful because it allows us to simplify the problem and yet not have to face a lot of numerical challenges that can come with those kinds of problems. So this is the Q-R factorization. It's used a lot when you have large matrices that you're dealing with. So these are all of our factorizations. So special matrices and factorizations. There's a lot of stuff we can do with matrices. A lot of tools available for us to use. And we'll pull out the tools as we need them.